Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler and today we're going to be doing Unit 8, Lesson number 3 on basic vector operations. Alright, so far we've learned the basic idea of vectors, right? And we've learned how to take them with their magnitude and their direction and break them into their component parts. And in the last lesson we reversed that. We took vectors and their component parts and we found their magnitudes and we found their directions. We know how to add vectors graphically by connecting them tail to head and then drawing in the resultant. Today what we're going to be doing is we're going to be looking at basic vector mechanics. Now or basic vector operations. And this is something that often happens in math when a new idea is put into place. You start trying to draw parallels between it and older ideas. So what we want to do is we want to see how vectors sometimes work like just normal numbers and sometimes they don't. So let's get right into it. Alright, so we've got two vectors in exercise 1 given, vector u and vector v. And what we want to do is we want to find out what their sum is, what their difference is, and what 5 times vector u is. Now, these operations are so easy that most of the time students can do them without any issue because their intuition is correct. So what I'm going to do is I'm going to pause the video for a second, or ask you to pause it, and see if you can figure out the answers to each one of these. All right, let's go through them. Got to grab my pen. We're ready to go? Yes, we are. All right, so if you said that u plus v was gotten by simply taking the x component of u and adding it to the x component of v and getting 1, well, you're correct. And if you said that adding the y component of u to the y component of v, you would also be correct. So u plus v is the vector 1i plus 12j. By the way, that kind of makes sense because if you really think about it, what u really is a vector that goes to the left 3 and then goes up 7, right? Giving us this resultant vector. I'm not going to do this for each one of them, but I'm going to try to make sense of this, right? Then if I were to add on v, what's v? v is now something that is 4 units to the right and 5 units up, right? And so here comes v, right? So overall, right, it makes sense then that u plus v would in net go 1 unit to the right and 12 units up, right? Simple enough. So that's really, really nice. It's almost like combining like terms. We combine the actions of the horizontal components, we combine the actions of the vertical components. This is where we go back to that first day when I said that, yeah, you can think of a vector as something with size and direction, magnitude and direction, but it's also good to think about vectors as things that can be broken down into independent component parts. Because then I can look at them and I can say, yeah, when I combine vector u and vector v, I'll combine their horizontal components and I'll combine their vertical components, then I'll leave them that way. Subtraction is much the same way. Of course, with subtraction, we also have to worry. And in fact, what we might say is that when we find u minus v, right, we're going to take negative 3 minus 4 and get negative 7. We're going to do 7 minus 5 and get positive 2. And it's that simple. I bet you got 5u as well, right? Because what 5u is going to literally be is it's going to be something like this. And we're just going to give the distributive property. Now again, I want you to really understand that. I'm not going to draw it completely out, but that should make sense. What 5u should really mean is u plus u plus u plus u plus u. Right? So we have negative 15 in the x direction, right? Because we just keep going to the left 3 units. And we have 35, etc., right? And then we have 35 in the y direction as we keep going up 7 units. Okay? Take a look at exercise 2. Gives us vectors in this kind of funky notation. 3-dimensional vectors, but whatever. Then it defines another vector, w, defined by 2u minus 3v, and then it asks you to find, well, what it asks you to find. I don't want to tell you that because I want you to be able to interpret that. I'd like you to pause the video and take oh, I don't know, maybe 5 minutes to figure this out, okay? All right, let's go through it. Now, a lot of students do this in a very incorrect way. All right, I'm going to do it in a very straightforward way. Okay, and then we'll take a look at some of the incorrect ways students tend to do it. All right, this is the magnitude of vector W. Now, we should know how to find the magnitude of a vector if we know the vector in component form. So the most straightforward way of doing this is to simply figure out what vector W is. In other words, vector W is twice vector U, and this is completely good, a really great way to write it, minus 3 times vector V. So, taking this to an extreme, I can say that this is 4, negative 6, 14. This is 3, negative 15, 3. And I can combine them to get the vector 1. Watch out here, negative 6 minus negative 15 would be a positive 9. I'm not going to put the plus there. Positive 9, and then I have 14 minus 3, which is 11. So this is vector W, right? So it's simple enough now to find the magnitude of vector W by doing our usual, where we, whoops, I'm going on a slant now, where we have square each one of the components, add them together. This turns out to be kind of ugly, but regardless, we have root 203. All right, root 203. So that's the correct answer, and it's very straightforward. If they ask you to find out how long a vector is, for goodness sakes, consider figuring out what the vector is in component form and then using that Pythagorean theorem method. On the other hand, here's what other people will do. Some people will do this. They'll go, well, all right, let me figure out the length of U. And they'll say, well, that's 4 plus 9 plus 49. So that's going to be 58, 62. Some people will then figure out the vector V, and they'll say, all right, that's 1 plus 25 plus 1 gives us root 27. And then they'll say, well, the length of W, therefore, must be equal to 2 times the length of U minus 3 times the length of V. And I just want to be very adamant to say that this is wrong. All right? Can't do that. In fact, the only way that would work is if vector U and vector V were collinear. If they pointed in the same direction, this would be maybe an okay approach. I always talk to my students by saying, look, this can't be the right approach. It can't be. Because with this approach, there's a chance that the size of vector W is negative. And the size of vectors is never negative. Now, we get lucky in this problem because it doesn't actually turn out to be a negative number, but it's close. In other words, we could very easily have this turn out to be negative, and it can't be. So don't invent things that you don't know, all right? Not unless you're absolutely sure about them. Anyway, I'm going to clear out the text, copy down anything you need to. Okay, let's get rid of it. Exercise number 3. All right. U equals 5a plus 3j, do the following. Letter A, sketch a diagram of this vector. All right, please pause the video and do that quickly. All right, let's sketch a diagram. We're going to go 5 to the right. I'm going to try to be relatively to scale here, so I'll make that 3 a little bit shorter. And this is vector U. Now it says, determine a formula for 2u and sketch its diagram. All right, pause the video while I change back to blue. Why don't you go ahead and do that? All right, should be simple enough, right? 2u will be 10i plus 6j, right? And that's what this is going to look like. Now, probably easy enough, what can you say about these two vectors, about the vector u and the vector 2u? Okay, what would you write down about those two? Well, what I'm hoping is you use the word parallel. right? They're parallel. They definitely are parallel. I mean, look, all 2u is, right, is this. There's 1u, and there's 2u, right? Plus, you could also think of them as having slopes of 3 divided by 5 and 6 divided by 10, respectively, so 3/5. So they're parallel. And that's kind of cool. It leads us to a very important thing. Whenever we take a vector and we multiply it by a positive constant, we get a vector that is twice that long, or 3 times that long, or 5 times that long, but points in exactly the same direction. Let's figure out letter D. Okay, please pause the video and do that. All right, well, simple enough. Negative u is going to be negative 5i minus 3j, all right? And its diagram is going to look like this. Right? And of course, here it is. Now, what's interesting about this is that in a certain sense, if we were just talking about coordinate geometry, we would say that negative u and u are also parallel. All right, they both have slopes of, 3/5. But this actually gets its own special name. This one is called anti-parallel. And again, I think it makes some sense, right? Vectors aren't lines. They're not lines. Vectors point in only one direction. So we really want to distinguish between two vectors that maybe look like this and are parallel, right? So these are parallel. And two vectors that might look like this, right? These are anti-parallel. Now, from just a pure slope perspective, they both have the same slopes, okay? But we do distinguish between two vectors that point in exactly the same direction and two vectors that point in exactly opposite directions. Okay, I'm going to clear this out. Okay, here it goes. All right, so the last thing that we're going to look today is a very practical application, all right, in terms of summing forces. And we're going to talk about what are called resultant forces. So just kind of a general discussion of this, because this is more sort of physics and engineering than anything else. When I take some kind of an object, like a mass, and I pull on it, or push, whatever. One person's push is another person's pull. But when I pull on it, let's say with a bunch of forces, what happens is that I can add all those forces together and sort of replace them with a single force known as the resultant, all right? Engineers and physicists do this all the time so that they can really look at an object and go, oh, that object is all in all experiencing a force of this many pounds in this direction. All right. Now, it's very, very, very easy to figure out resultant forces because all they are is the sum of all the individual forces. But that's only helpful if they're broken into component parts. That's the key. So to find resultant forces, what we always need to do is break individual forces down. Break individual forces into components. All right. Now remember, in general, what we saw was that if I take just a generic vector v, right, I can always break it down into its component parts by doing v, the size of v times cosine theta, that will be the horizontal component, and the size of v times sine theta, that will be the vertical component. All right. So let's take a look. Two of these three forces are actually quite easy. For instance, F1, right? Notice F1 in its component has absolutely no horizontal component. So I'm going to actually write that as 0i. Now you have to be careful. Its vertical component is negative, right? It's pulling downward, so it's negative 8j. So that's pretty easy. Force 2, that's also very simple, right? It's pulling strictly in the horizontal direction and in the positive horizontal direction. So it's 3i plus 0j. All right. Finally, force 3, we actually have to do a little work, right? And the reason that we have to do a little work is that theta, right, that theta in this decomposition formula is always the angle from due east. So what we really have to keep our eye on the ball here is that it's not about the 20, it's about the 160. Oops. So F3 is going to be equal to 7 times the cosine of 160, I, plus 7 times the sine of 160, J. Now, I would not evaluate this at this point. I wouldn't evaluate it. I'd leave it that way. Because the resultant force, F sub capital R, is going to be adding up all the horizontal components, so that'll be 3 plus 7 times the cosine of 160. Don't make that into 10 cosine 160, right? Plus, now let's see, negative 8 plus 7 times the sine of 160. This is actually quite good. This is as good of a form as you really get because it's exact. That is the exact resultant force. Now, if we really want to do anything with it, if we want to be able to think about it, figure out its size, all of that kind of stuff, then I actually have to work out the numbers. So the resultant force, right, FR, and I can't do this in my head, and it's awfully ugly. I'm going to put it in this form. It's negative 3.5778 and negative 5.605. All right, so think about that actually. We have a force that is pulling us to the left and pulling us down, right? So we have this net resultant force. Now the problem asks me to do two things, really. I got to find the magnitude of this force, and I have to find its direction angle. But that's what we did last time. So what I'd like you to do is now pause the video, work through it all, try to come up with your resultant force. As a suggestion, you may want to, use your calculator and, maybe store this in A and store this in B. That's up to you and how you use your calculator to deal with messy numbers. But it's really, really helpful if you've got these stored. All right, but take a little bit of time, try to figure out both the magnitude with units and the direction with the positive x-axis. Pause the video. Let's go through it. All right, well, it should be simple enough, right? The magnitude of F sub R, all right, is going to be, and I'm going to use those letters A and B because I've already designated them as such and it's messy. So I'm going to square that component, add them together, take the square root, and I'm going to get 6.650 pounds. So there's my magnitude. Now, in order to figure out the angle, right, this also takes us back to yesterday. I'll probably figure out a reference angle first. So I might say something like the tangent of alpha is equal to, 5.605, right, the positive version divided by the positive version, 0.5778. I can figure out that alpha then is, sorry, I'm taking up all this room, is 57.452, etc. And then the actual angle I care about will be alpha plus 180, which will be 237.452. There we go. This is great. Engineers do this all the time. Oftentimes when they analyze bridges, simple bridge structures, what are known as trusses, they don't even have to be bridges. They could just be like in a person's attic, a simple truss system. Right, every one of what are called nodes, these intersection points, they have to sum resultant forces, or they have to sum forces to get resultants. Oftentimes, setting up humongous systems of equations with unknowns. But let's pause there. Copy down anything you need to. All right, let's do the last problem. In the last problem, we've got a ball or something, and we've got two forces that are known and one force that's unknown. But the problem says that the object has a net resultant force of 0 acting on it. So this is what happens when an object has 0 acceleration. I was just about to say it's what happens when an object isn't moving, but really an object could be moving, it would just have to have a constant velocity. So anyway, sorry, the physicist taking over. So I got this object, a net force of 0 is acting on it. I want to figure out force 3. I want to figure out its magnitude and the direction it makes with the positive x-axis. So here's what I know. I know that when I take force 1 and I add force 2 and I add force 3, it's not that I get 0, but what I get is I get the 0 vector. Okay, I can't set it equal to 0. It doesn't really make sense to add a bunch of vectors together and get 0. That doesn't make any sense. All right, but let's see what we can do, right? Force 1 we can say is, let me go with this notation, -8, 0. Good enough? Force 2, on the other hand, beautiful arrow there. Well, that's going to be 5 times the cosine of 40 and 5 times the sine of 40, right? And then force 3, well, I don't know. I could use some letters down here. I could use x, y. Typically what will happen is this is the way it'll be denoted. Force 3x, force 3y. Notice I've left the arrows off the top. The reason for that being that they're now scalars. I know this looks terrible with all the commas, right? It's kind of like a big comma, right? The point is, what I can now say is that when I add the x components together, right? When I add these components together, they all have to sum to 0. That's easy, right? That now allows me to solve for the x component of force 3. That would be 8 minus 5 times the cosine of 40. That would be its exact value. But then when I work it all out, where is it? 4.1697. I can do the same thing for the y coordinate. That's easy enough. I can say that 0 plus 5 sine 40 plus force 3 in the y direction is equal to 0. Silent communication. So force 3 in the y direction is -5 times the sine of 40, which would be -3.2139. So I have force 3, at least in its component parts, right? And it's ugly again. Most of these problems don't turn out nice. 4.1697 and -3.2139. And now I can do exactly what I did last time. In other words, I need to figure out its magnitude. I need to find its direction. Again, I'd ask you to pause the video and figure those out for yourself. All right, let's go through them again. Again, great idea because of how messy the math is at this point. You know, you store this like in letter A, you store this in letter B. To me, that's a lot easier because then, you know, you can square both of them, add them together. Either way, again, I'm not going to go through the math on that. We did that a lot last time. We end up to the nearest tenth getting 5.3 pounds, right? Then the direction vector, again, this gets a little bit sloppier because, you know, you've got to set up that right triangle. Well, actually, I can set it up in blue, right? You've got that 4.167, and then we're going down, so we've got 3.2139, right? I can figure out my reference angle by setting up the tangent ratio again. One thing that's nice about this is that it is very repetitive, which means that eventually you just get really good at it. My reference angle ends up being something like 50. Whoop, no, that was my reference angle last time. Wrong problem. Sorry. My reference angle ends up being, I hope I didn't just write down the wrong thing. My reference angle ends up being 52.37 degrees. And therefore, the actual angle I care about, which is this beast, is 360 minus that, right? And that would be 307.6 degrees. So it's kind of neat, you know, and this is actually what engineers do a lot, especially when they're working in the area of what's called statics. Statics is they say, oh, I have an object, and it's not moving. That means that the sum of the forces on that object must be equal to 0. Well, I know this force, and I know this force, which means I can calculate some unknown force. Very, very often. And again, the key there is to have those forces broken down into their individual horizontal and vertical components. If we were in 3 dimensions, we'd be looking to break them down into their x component, their y component, and their z component. But that is, in a certain sense, out of the scope of this course. Okay, so I'm going to clear out the text. Why don't you go ahead and copy it down. Cleared, and let's finish up. Okay, so now we've gotten vectors, we've gotten a feel for them, we've gotten their notation, we understand kind of a little bit how they add and how you can multiply by a scalar, right? We've also seen how we can combine all of these skills in order to work with resultant forces on a body. Okay. We will now push this in future lessons in terms of what's known as the dot product of vectors, and that's where it really starts to get kind of fun for me. But until that time, let me remind you, this has been an Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.